Okay, so again, when we do priorities for these things, whenever we're doing the EZ or the RS and we're trying to figure out what has higher priority, we always do it in a round robin. Okay, so we radiate out from the group that we're looking at. In this case, that would be here, right? And that would be our chiral center. And what we would do is we'd go the first option, the highest priority. Which one has highest priority between those? Okay. And then we would go the next option after that, the next option after that. Okay. Now remember, you have to go through all the groups bonded to it. Okay. So for example, this first option would be the carbon, right? And then what we do is we go through the options off of this carbon. Okay. In the case of a double and triple bond, those are going to have multiples of the same group attached, right? Another way of thinking of that is because the double or triple bond, we don't have as many groups attached, right? And so those slots will be taken up by whatever the double or triple bond is attached to, okay? So for example, this carbon here is going to count as if it has 2 carbons attached directly to it and a hydrogen. And so we'd go down the priority, carbon, carbon, and then hydrogen as we compare things round robin. Over here, we would have 2 nitrogens attached to this carbon. See that? Because the double bond. So we just count that nitrogen twice. Everybody okay with that so far? Now, if we have to go on to the next priority, so if, let's say, we still tied to whatever we're comparing it to here, okay, when we're attached to this carbon. Okay, so what we would do is we'd go on to the next attached thing, which would be the nitrogen, right? And then we'd count off, well, we'd do a carbon, another carbon, and then a hydrogen. Okay? And so remember, I'm going to give you some examples in a bit, but remember those double bonds, you just count whatever it's attached twice. Okay? Okay. This is an oxygen double bond that's going to have 2 oxygens then attached to this side. This side will count as if it has 2 carbons attached. Okay? Triple bond is just going to be counting the other thing 3 times, right? It's triple bonded. Okay. All right, so let's go ahead and try this out. Right here, we have our chiral center. And so we're going to figure out what has highest priority around the carbon center. The hydrogen is already facing away from us towards the back, right? So thank goodness. We already have our lowest priority in the correct space. The next thing we're going to do is we're going to go out from here and compare each of these. So we have a carbon attached to this, a carbon attached here, and a carbon attached here. They're equal, aren't they? And so currently we can't make a decision. Then we're going to look at the things that are attached to them. And so then the thing that's attached to this one is that carbon there, right? That's your highest priority. This one has a carbon attached to it. And this one, no carbon. So that's our next lowest priority, isn't it? It'd be a carbons versus hydrogen there. And so hydrogen has lower priority, and that's priority 3 there. Okay? Okay, so we're still tied for these 2, aren't we? Right? This one, we ran out of carbons, didn't we? So we have to go to the hydrogen now. That's the next to highest priority on this one. This one, on the other hand, because of the double bond, we count the carbon twice. Okay? And so this one's now going to win the priority war, right? Because we count the carbon twice due to the double bond. Everybody okay with that so far? Okay. Remember that, yes, it's in terms of molecular weight, but round robin molecular weight. Not total molecular weight for the entire thing. Okay? So we go through on each point of attachment and go, what has the higher molecular weight? What is going to be our higher priority? Is that making sense so far? You do. Yeah. So like if we had a triple bond over here, this would end up beating the double bond in this case. Yeah. So the triple bond, count 3 times. Okay. So the 4th priority substituent points towards you in cases that are not like this. So this is pointing away from you. So your assigning R versus S is quite simple, isn't it? Because we just have to figure out what the priorities are, and then from there, we trace them out. So it'd be this way. Everybody okay with that so far? But what if the hydrogen here was put in the wedge? It was pointing towards you instead of away from you. Well, then when we try to trace this out, we're going to be messed up, aren't we? It'd be looking at your right hand versus your left hand, right? See that? They look like mirror images, right? Exactly. I'm looking backwards, aren't I? So in the cases where we have the hydrogen, instead of being faced away from you like it should be, it's faced towards you. Well, you're just looking at the exact mirror image reflection, aren't you? And so you don't actually have to redraw it. You can just assign it normally. And whatever you come up with, you're going to have the exact reverse. Because you're looking at the mirror image, aren't you? Okay? And so if you do the assignment and the hydrogen happens to be pointing out towards you, and you get an R, then the actual assignment was an S, wasn't it? Because I did it backwards. Okay? If I do it when I'm looking down the opposite direction, and I got an S, counterclockwise, right? Then that means the actual assignment was the exact reverse, wasn't it? Okay? Okay. So again, that's in cases where your hydrogen is pointing straight out towards you, okay? That's actually the second easiest case. Yes, it's the opposite. Hydrogen is pointing away from you. It's just S. That's what it is. Yeah, hydrogen should be pointing away. If the hydrogen is pointing towards you instead, the exact opposite, then your assignment is the exact opposite. So instead of being S, when it was pointing away from you, exactly, you're looking at exactly opposite, right? And so all you need to do is just flip your assignment. That's it. Okay? You don't have to do any rewriting or anything. Mm-hmm. The R and the S is the rotation. So it's the clockwise versus counterclockwise. So for example, this right here, this was highest priority, right? Second highest, third highest. And so see how that's counterclockwise? That would be have an S designation. Okay? Counterclockwise. R, like right hand, right? Clockwise. And this is telling you which of the two possible chiralities you have. It's like saying right versus left. Yeah. And these are absolute orientations. Because of those priorities we give, no matter what direction it's facing, we can always do this. Okay? Very, 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 very simple. The LD, though, are different enantiomers. Okay. But same, that rotation around the last one, that OH, is setting that, yes. Yeah, that is the same thing. The problem with LD, though, because you're doing it in Fisher projections all the time, it doesn't actually correspond to any physical properties at all. Because that you've abstracted it so much. So like you could have an R that's a D in one case, and an S that's a D in another case for a different sugar. So they don't directly correspond. But yes, D and L is just an alternative way of doing R and S for different enantiomers of sugars. Does that make sense? Yeah, so like if you have a D against the R, if you were then to get the L, that would be the S. Okay, and that one also would be an absolute, by the way, orientation, because you have very specific rules set Fisher projections. So, okay. Okay, so the other one that we need to look at here is, what if they're not on the in out of the plane? Okay, what if that hydrogen is not on the in and out of the plane? Okay, so if your fourth priority substituent is actually in the plane of the page, then you're going to exchange the fourth priority substituent with the substituent that points away from you. So you can get it in the one that's I'm just going to erase. I'm literally going to erase the fluorine, erase the hydrogen, and swap them. It would be the equivalent of you pulling the model's chlorine off and hydrogen off and swapping it. Yeah. It won't be the same as rotating the model. Yes, technically, you're actually making the other chirality. So if this was an enantiomer, this would be the two different enantiomers. And that's why you're going to actually be flipping its R and S. Okay? So you're going to exchange it with the one that points away. Then you're going to take the first, second, and third priority substituents. You're going to see if they're arranged clockwise or counterclockwise. And then you're going to reverse that arrangement. Because you've literally taken the groups by exchanging two of them, and you've actually swapped it to the other enantiomer. Okay? That's literally what you did. That's how you would draw the other enantiomer, right? Remember how I was talking about, this is how you draw the other enantiomer. You literally take two of the options, and you swap them, right? So we took two of those options, and we swapped them, didn't we? Okay? Remember, you always want to do it in the plane of the page. This actually doesn't work as well if we do it the other way. It can actually cause thought problems. It's actually kind of difficult to do. Okay? And the reason for that is, if we remember our tetrahedral structure, is there any difference between these two? No, they're the exact same thing, right? So if you swap from this position to this position, it's different. Sometimes if we swap these positions, we can have no difference. Okay? So sometimes when we swap the in and out of the page, it can actually not help us. Right? That's why you never want to swap it. You just want to assign it R and S, and then it's the other one. Okay? Because remember that, like, let's think about that for a second. Are those different things? Not at all, right? Not at all. And the reason they're not different things is these were never oriented differently in this direction, were they? At all. These were oriented in this direction, weren't they? So you writing it on the left or right had no meaning. Okay? All that had meaning was that it was the tetrahedral. And so these were down like this, these were up like this. And that's it. Whether you write it like that or like that, had no meaning. Okay? Okay, so you gotta watch out for that. Remember, it's the three set of rules, right? If hydrogen's facing away from you, what do? Just priorities, right? Just assign your priorities, clockwise or counterclockwise S. Okay? If hydrogen's pointing towards you instead, again, just assign your priorities. Clockwise R, counterclockwise S, but you do one more step. You got an R, the actual answer is going to be S. You got an S, your actual answer is R. And again, that's if hydrogen is pointing towards you. If hydrogen's in the plane, these positions, that's when you're going to take your structure. You're just going to erase the one that's away from you, erase the one that's in the plane, and swap them. Okay? You having done that swap means you automatically have flipped your chirality. Okay? And so you have flipped your chirality, you assign it same sort of priorities as you would have before, and then again, you're going to flip that chirality. Okay? Don't forget to do the swap. Things will get very confusing very quickly if you forget to do the swap. Okay? Okay. Let's look at some examples real quick. So again, we assigned our chiralities here, and then we looked at this and see that hydrogen, that fourth priority one, that's pointing towards you, isn't it? Okay. And so it should have been R, right? But what is it actually? S. Yeah, it's actually the S, isn't it? Okay. Remember that lowest priority one, you never count it. Okay, because it's supposed to be away from you, invisible, lined up behind the other carbon, right? Okay. So this one right here is one where, see that hydrogen, that fourth priority one? That's in the plane, isn't it? Okay. And so what we're going to do is we're going to swap it with whatever is the one in the back away from you. Okay. And so that's the chlorine in this case. So we redraw it with the hydrogen and the chlorine swapped. Everything else is the same. Okay. And then we assign our priorities. Chlorine's the highest, this one's the next highest, and that one's the final highest. Okay. And it's this direction, so that would normally be S. But its actual priority now, because we swapped those, R. That's the actual answer. Is that making sense? If you remember those rules and you remember how to do the priorities, these are actually fairly simple. Yeah. Right here? Here? Because it's not chiral. So our center carbon is always the chiral carbon, because we're trying to assign the different enantiomers for that chirality. Does that make sense? Okay. And if you did have more than one chiral center, then you'd actually need to do that for each chiral center. And so whatever your chiral center that you're looking at in that case, that's the one that's going to be in the center. And you're going to branch out from that to figure out priority. So let's say we had another chiral center like over here. We would do this another time, this whole thing, and we branch out from it. Okay? That makes sense? Okay. Very good. So, by the way, what if we don't have a hydrogen that's expressly written in a structure? What do we do with that? Yeah. What we need to do is we need to look at all the other stuff, right? So if the chlorine is pointing out towards you, then where's the hydrogen if it wasn't written out? Yeah, it's behind, isn't it? And so you're good. You can just use that. No problem. Okay. What if we had two structures here where we had in and out for everything else, but we don't have the hydrogen listed here? Well, then that would be in the plane, wouldn't it? It's the only other position. Okay. So you can always rewrite them to express those hydrogens. Just remember that it has to be whatever position hasn't been taken. Okay? Okay. Got everything that everybody gets confused about. All right, so let's talk about mirror images that can rapidly interconvert. If you have a single bond, this is going to be a rapid interconversion. And so they are going to continuously be spinning around that single bond, just like a nice axis, right? Like it doesn't take much effort to rotate this, right? And so I would not act like some part of this structure is always going to be visible to you, would I? Because I can just rotate it very easily the other way. Okay? And when you're at room temperature, these single bond rotations are happening all the time, just constantly, like a little propeller. Okay? And so these are why these are called conformers, and they're not called the same sort of isomer terminology that we've been using, right? They're not enantiomers, they're not diisomers. They're conformers instead, because they're going to be rapidly interconverting. We can't effectively take one and get it to the some state that we could actually like identify it or test it. And so we consider those achiral. Okay. So for example, you look over here, yeah, these have different conformers, right? And they have mirror images, they're non-superimposable when you look at those gauche conformers, don't you? Okay. But the problem is that you couldn't isolate that and test it. You couldn't react that and only get one thing. This is a conformer. It's going to be interchanging all the time. Okay? Does that make sense? Okay. Just like I don't like consider this hand and this hand different hands, right? I have 100 hands. No, that's not how terminology works, is it? Okay, so this would be another rotation. You can see we can interconvert very easily. There is an energy barrier there, but it's very small, right? Okay, so again, those would be achiral carbons. This right here would be the chair flip, and this is why that's oftentimes not considered different stereoisomers, right? Is because you can actually have the chair interconvert and flip back and forth. Okay, and again, those are different conformers, aren't they? Rather than being different diisomers of each other, or different enantiomers, depending on. So again, these would be your different chair flips. Notice again, if we do this chair flip, we just do a 120 rotation, we actually get the exact same structure. There is no difference. Okay? Okay. All right, so let's talk about Hawthorne projections. You've actually seen Hawthorne projections quite often. You just didn't realize that that's what they're called. They're very helpful for determining the chirality of cyclic molecules because you can write them in such a way that they'd actually be something similar to the priorities you'd need to deal with. So they're going to simplify your chair conformation of the cyclohexane to just a flat hexagon. And this is going to allow us to quickly and accurately determine your chiralities, achiral, and to assign priorities. So we can figure out if it's R and S if we need to. And so this right here is your CIFs. And notice we have the plane of symmetry right here. And again, this is the Hawthorne projection, where we're projecting the ring as if it's flat, pointing out towards you, right? And you've seen that a number of times now. You just didn't realize it. Okay. So if we look at these Hawthorne projections, we can very quickly see like planes of symmetry, whether they're cis or trans. Whereas like the axial diaxial, you had to go through a process, right? When we were looking at these chair conformation rates. And I've given you enough homework that you probably were like, thank goodness we have Hawthorne projections. I'd hate to do that every time. Chair conformation. So this right here is the trans. You can notice here in the cis, we actually have a mirror plane of symmetry, right? And in the trans 1, 2, we don't have a plane of symmetry. Okay, it's not symmetric either way we place that plane. And so that actually gives us the ability to make this different stereoisomers with those, right? Okay, this is the nitrogen inversion. This is a little bit interesting and kind of unique. You may not have realized this from the nitrogen inversions. You may have went, Dr. Clausen, there's 4 things around that nitrogen. There's a lone pair, right? The problem is lone pairs can move back and forth very easily. Lone pairs are just electrons, right? Like if I went, okay, you're stuck because there's a marker here and you have to pull the marker. You're not stuck, are you? Take the marker and go, right? If it's not weighted enough, it's going to interconvert all the time. Okay? And this is the same sort of thing with this. These nitrogen, these electrons are just so easy to move around the nucleus, and they're so light that this doesn't take a lot of energy. It's not the sort of energy with breaking bonds, right? And so we get interconversions here. These are the inversions, okay? Where the nitrogen literally, like, those 2-sided like shirts or beanies, you can just pull the middle and it's the other one. They can do the same sort of thing. So they can just interconvert between the 2 possible, what would have been your enantiomers, right? Your super images that were non-superimposable. Okay? And yeah, they can have mirror images that are non-superimposable, but the problem is that they would interconvert at room temperature all the time, and so they just aren't fixed that way at all. Okay? These would actually be 2 different conformations of this. And so nitrogen inversions, these are not chiral centers because they can interconvert all the time. Unless you have an actual bond on that 4th position, it's not going to be a chiral center. Okay. This is actually why that happens. So remember, these are these sp3 hybridizations. What are they actually made of? Well, they're made of those s and p orbitals, aren't they? So what can happen here in this lone pair is, again, we don't have a nucleus there. These electrons can move around really easy. And so this can actually go back to its unhybridized p orbitals. If you have enough energy difference or enough energy available, it's going to actually do that fairly often. Okay. And so at room temperature, this actually happens quite often. At least millions of times a second sort of stuff. Okay. So this right here, what happens is it unhybridizes. That gives you the planar structure right here. And then we have the electrons in one phase of the orbitals, right? Well, then they can just go pop over to the other phase of the orbital. Okay? When it rehybridizes, you're going to get the inversion, aren't you? Right? And so it's just going to pop back and forth all the time. Interesting little factoid. If you got the temperatures low enough, you might actually be able to stop this. It depends on the sort of energy barrier you're looking at. But yeah, you can actually freeze conformers in place, at least temporarily. Because they do have an activation energy. We just consider that activation energy negligible because at room temperature or even ice bath temperatures, you'll have interconversions fairly often. It's one of the things I used to do in my graduate studies, in case you're curious. I make very low temperature solutions of noble gases. And then you can study the different conformations. Okay, so diisomers is going to be stereoisomers. They're not mirror images of each other, though. Okay, that's the difference between like an enantiomer, right? Enantiomer stereo images are mirror images of each other that are non-superimposable. Diisomers, on the other hand, these are going to be stereoisomers that are not mirror images of each other. Okay, still non-superimposable though. So cis and trans were examples of stereoisomers. So here we have the cis dichloroethene. Here we have the trans dichloroethene. And again, they are very clearly not mirror images of each other, right? Yeah. Again, they have to have the same molecular formula, same connectivity, but not mirror images of each other. They are different molecules. They will have different biological effects. They can have different polar, non-polar behaviors. Like these right here would have a different non-polar, polar behavior. Okay? And so they'd actually have different melting points. Now, cis and trans, remember how I was always going, you need to say with respect to. Okay? So this is cis with respect to the chlorines, right? Okay? If I don't put that, then you really don't know what it is. If I was saying this chlorine is cis with respect to hydrogen, well, that's this one over here, isn't it? Okay? And so all of a sudden, I've lost the meaning of my cis and trans. So cis and trans don't have an absolute meaning. Okay? So we have a system that is for these double bonds and rings that is going to be absolute. It's going to use that same priority system. And so then we always have a higher priority. When we have the higher priority on the same side, those are going to be on the same side. Okay? And so it's Z. Everybody want to do that with me? Remember it? On the same side is Z. Okay? On the same side. If you trust me, it's worth the embarrassment. When you get on the exam, you're going to be a lot more embarrassed that you don't remember EZ. And I will literally promise you, there'll be somebody, at least one or two of you, during the exam, that's like, on the same side. And then gets the problem right. Because it works. It's easy, right? E, on the other hand, these are going to be the opposite sides of that double bond or ring. And so your higher priority ones are on opposite sides. Interestingly enough, I typically remember this because E has a little part in the middle, right? And then two parts on the opposite sides of it. And so that's how I always used to remember it when I was in your position. Is E to me looks like it's denoting two different sides of an item, right? But on the same side is by far away the more effective thing, which is why I use it. So remember, you're going to assign your priorities on each side of that double bond, and then you're going to assign it Z, same side, E, opposite sides of the double bond. Okay. Okay, does anybody have any questions about that so far? Let's try it out. So, what's the higher priority between chlorine and carbon? Chlorine. What's the higher priority over here between carbon and hydrogen? Carbon. And so our highest priority ones are same side, and so that is Z. Yeah, so we don't actually care. We just care about highest priority on each side. Exactly. So all we care about is this one over here, this set, which is the highest priority. Over here, what is the highest priority? The chlorine. Chlorine is a higher mass than carbon. Remember, you do it round robin. You do it round robin. So it's only the ones that are attached that you ever look at. So chlorine versus the carbon here, and the chlorine wins. If we were to compare like two CH groups, then we go down the list. Round robin. Okay, we look here. This is going to be the E because these two highest priority groups are on opposite sides. Anybody got that okay? And remember again, round robin. Here we have a ring. Now notice these rings here are going to be diisomers. They don't have a double bond, and that's because they're fixed in place by the ring, aren't they? Okay. And so these right here, these would be diisomers of each other. Now, if two isomers are related by reversing the configurations of all the chiral centers, then the two molecules would be enantiomers, assuming they're non-superimposable. Okay? So if you reverse all of your chiral centers, they would be enantiomers. That's the DNLs, by the way. Those are enantiomers where you've reversed all of your chiral centers. Okay? If you just reverse one of those, that would be like saying glucose versus the other sugars that are 6-membered. They're stereoisomers of each other. Diisomers, in fact. Okay. So this is that same problem we've done before. I want you to go ahead and draw out the possible options here. There's more than one option. So if you've only gotten one, bless you. In case you're wondering, the sugars have 8 different ones for 6-member, and how you always do that for the chiral centers is it's 2 to the power number of chiral centers for the sugars. And so there's 16 possible arrangements of the sugars for a 6-membered sugar, 6-carbon sugar. And you only need to, or 16, excuse me. Only need to count up 8. Because the other 8 are the DL enantiomers. Okay, let's go ahead and move forward here. All right, so what do you need to do here? Well, the first thing you need is the chiral centers, right? So you find your chiral centers. Is this a chiral center? That one? This one? This one? That one? How do I figure out how many possible different stereoisomers there are for this? Yep. So 2 to the power of 3 in this case, right? And so now how do I figure out the other diisomers of this? Well, I want to avoid the enantiomer, so don't flip all. And what you want to do is you typically want to start with just flipping one. Okay. And so we're going to take our one that we're given, and we're going to flip one of those. See, I flipped the top. Okay. And so now that's a diisomer of it. Okay. And then I go and I flip the next one. And that's going to be a diisomer of that again. Okay. I could also flip 2, and that'd be another diisomer. Okay. That'd be a stereoisomer of the first one. If I flip all of them and it's still non-superimposable, that would be an enantiomer, right? So if I did away, away, towards me. Okay, so what are some of the drawing strategies for success when we're trying to figure out all the stereoisomers of a molecule with chiral centers? Okay, so a new configurational isomer can be obtained with each inversion of a tetrahedral stereocenters conversion. The number of configurational isomers that exist can double with the addition of each chiral center. And so we do 2 to the power of n, 2 being that has 2 options, right? And n being the number of chiral centers. So this number actually represents the maximum because it does depend on the symmetry of the molecule. So for example, like I have right here a point where I have symmetry, don't I? And so if I flip all of my stereocenters, I actually end up with an exactly symmetric, don't I? I end up with a superimposable mirror image and end up with not an enantiomer or anything. Okay? And so this is always the maximum. You are not guaranteed to get all of these. Okay? The number is going to represent, again, maximum. Some of those RS combinations end up meso. And if you have a meso, that means the other one's the same molecule, right? When you flip them all. Now, you identify all the chiral centers first. You draw the first structure by specifying the configuration of every chiral center. Use your wedge dash notation to specify each configuration for your first structure. Honestly, in this case, when you're just starting out, it really doesn't matter which one you choose. Just start and commit to a choice. Okay? This is actually a place where people have a lot of problems. Like they just get like, which one should I start with? There's so many possibilities. Just pick one, doesn't matter, start. Okay? Okay, so then you draw the second structure, and all you have to do here is reverse the configuration only at chiral center 1. The first one that you drew up on the top left, there you go. Okay? And then the next thing you're going to do is draw the next 2 structures by reversing the configuration of chiral center at your 2. Okay? So you take what you just drew, you copy and paste it, and then you take those and you reverse the second center. Okay? And then you're going to do the same thing for the next 4 structures by reversing the configuration for your next center. And you'll keep doing that till you run out of chiral centers. Okay? That will do all of the possible 2 to the n power, right? And so now I have my 2 to the n powers. All of those are done. Okay? So the next thing I'm going to do is I'm then going to look for the redundant structures, the ones that are the same thing, and I'm going to get rid of the redundant structures. Those are going to be omitted from my final answer. Okay? When you do this on like an exam or on exam, if you do this with pencil, you can erase them. If you do it with pen, just put a circle and strike. That's not one. Okay? If you do this on your computer, you just highlight and delete, right? Okay, let's try it out. So see, we have here 3 chiral centers. Are we okay with that so far? We haven't drawn out any chirality yet because we don't have any wedge dash notation. Okay. Now, how many possible configurational isomers are there going to be? Well, there's going to be 2 to the 3rd power, right? 2 times 2, 4. 2 times 4, 8. It is, yeah. Because we always have 2 options, right? Could be R, could be S. Okay. And so it could be R here, S here, could be R here, S here. And that means it's always like a coin, right? That'd be the same math, by the way, if you were like, how many possible combinations of heads and tails would I make? That'd be your number of coin flips. Okay. So this right here is going to be the first step. I choose one. Most people like to choose out towards them, the bold, wedges. It just makes them feel better, I guess. I guess probably because I train you to put the least priority away, right? That's probably why. Anyways, so this is your first one. And then what do? Well, we flip it, right? And we get our second one. Now, once we have 2 of them, we're just going to double that up every time and flip the next one. Okay? So we double that up. That's this right here, right? And this one right here. See those okay? And then we flipped this bromine here. We flipped that bromine. That's that second position. Then what we're going to do is we're going to double that up again, and we're going to flip the third one. Okay? And so this is these doubled up, and we flip the third one. Okay? This one here is these doubled up, and we flip the third one. Okay? And then those are all of our possible configurations. Okay? Now there could be ones that are the same one, right? In this case, we don't have a lot of symmetry or anything going on, so. But if we have enough symmetry, we can actually get the same thing. Okay, so there's actually 2 conventions for drawing Fisher projections. That's what we were talking about, the sugar. Those were Fisher projections. And so the intersection of the horizontal line and the vertical line, this is going to actually indicate your chiral carbons here. Those are going to be your asymmetric carbons. So when you see 2 lines crossing in a Fisher projection, this will indicate that chiral carbon, asymmetric carbon there in the middle. So the substituents on the horizontal bonds are going to point towards you. And you can think of it a lot like a bow tie. Okay? So it's pointing towards you like this. Right? That's the horizontal line. Okay? The vertical line, on the other hand, is pointing this way, away from you. Right? And so what you're seeing is in the Fisher projection is basically if you just took your structure and you oriented it in such a way that you're basically like looking down. So a normal chain would be zigzag, right? So it'd be this, then this, then this, then this, right? And so you're orienting it so you're looking like this always. Okay? So basically you're flipping back and forth as you go down the chain. And this is why if you ever do a Fisher projection, assigning R and S is incredibly difficult. It just becomes almost impossible to assign R and S in a Fisher projection. You can do it for one, then all the other ones become impossible. But there is tricks to do it. We'll see if I have time. Not that you particularly. Anyways, that's your tetrahedral. Again, the vertical ones here pointing away from you, right? Horizontal. Okay. So, exchanging the 2 substituents on an asymmetric carbon in a Fisher projection will always give you the opposite stereochemical or configuration. So if we take this Fisher projection here and we rotate it 90 degrees, that's always going to give you the exact opposite enantiomer here. Okay? If we rotate a Fisher projection 90 degrees in the same plane, that'll give you the opposite stereochemical configuration. Again, see that these are non-superimposable. mirror images of each other because we've rotated that. Okay. Basically, we flipped what was going in and out and what was coming out towards us, right? So, okay. All right, so these right here, this is Allose, by the way. This one is D-glucose. The D and L actually come from this last asymmetric carbon right here. Okay? And so D means it's on the right side. L means it's on the left side here. If you were to swap one of these groups, you would get a different name. Okay? So see here, these are both Ds. But we swapped this OH right here. And so we get glucose versus allose. Everybody okay with that so far? Okay. So these two are actually diisomers of each other, aren't they? We've swapped one of the chiral centers, or multiple chiral centers, and we get diisomers, right? But they're not mirror images of each other, so they're not enantiomers, right? If we swap and give the mirror image to each other, then that would be enantiomers, wouldn't it? And that's where we take all the chiral centers and we swap them. So every single chiral center gets swapped back and forth here. Everybody okay with that so far? Okay. Notice that that's actually sort of the same thing we were talking about when we were talking about like swapping the hydrogen, the opposite sides. Yeah. Okay, very similar concept, right? Okay, and so that actually gives us the D and L. So D and L's are enantiomers. When we have the different names for sugars, they're actually the diisomers. Okay, the different stereoisomers. Okay. Now, the vertical bonds in the Fischer projection are always going to point away from you. Horizontal bond always points towards you. One of the things you have to remember in a Fischer projection is that in a Fischer projection, you always are going to put the most oxidized carbon on the top. Okay? So the aldehyde or ketone always goes as far to the top as you can get, right? And then the non-aldehyde or ketone, the alcohol, always goes on the bottom. Okay? And that's why these always look similar, because you always orient that aldehyde or ketone. Okay, so what's going to happen here is this is how you actually get the R and S for a Fischer projection. Okay, and it's going to have a little bit of rules that we have to understand. Okay, so again, the vertical bonds is always going to point towards you in a Fischer projection. I'm sorry, the vertical point away from you, the horizontal point towards you. My mouth went ahead of my what I was saying. So again, horizontal points towards you, right? Vertical points away from you. Okay. Everybody good with what they're looking at there? Okay. So once we assign our priorities here, right? Remember, this hydrogen here is pointing towards you, isn't it? Okay. It's not pointing away from you, right? So when we assign these priorities here, we would have a counterclockwise. This would be our highest priority, second highest priority, because the oxygen here, and then third highest priority here. We never count the hydrogen, right? Even though it's pointing towards you, whatever. Okay. Okay. And so we would have counterclockwise, right? But what do we know about this hydrogen? Well, it's pointing towards us. Yeah, so we're going to have to flip this to the R clockwise. Okay. Now, this right here would be our zigzag conformation with our wedge and dash, right? And that's how we're used to looking at these so far. Now, what if we want to make this into a Fischer projection? How do we do that? Well, what we're going to have to do is we're going to have to do a bit of rotation, aren't we? So the first thing we need to do is we need to take this carbon right here that has the carboxylic acid, the most oxidized group. We put that on the top of our Fischer projection. Okay? That one has their highest priority, and that one goes on the top. Okay. From there, this backbone here is going to be pointing downwards, going on to this group right here, which has the OH. Notice that's a symmetric carbon. It's not a stereocenter, right? Not chiral. Because it has the two hydrogens. Okay, now we have our numbering, 1, 2, 3 through 5, right? So we're going to go down 1. The second one is asymmetric, and so that gets across. Third one is asymmetric, so that gets across. And the fourth one is asymmetric again, so that one gets across again, right? And those are telling us, hey, those are our stereocenters. These are our chiral carbons, right? Those are the ones we have to look out for, okay? Notice we have not yet actually assigned these the OH groups, have we? See how that we very, very purposefully avoided that so far, okay? We're just getting our backbone ready. Okay, everybody got your backbone? Ready to go? Yeah. Okay. So remember again, your asymmetric carbon is going to end up on the peak, right? And so what we do is we have to do 2 rotations for most of these structures. We do a rotation to put it in the vertical direction, right? But that would actually just leave us in the plane still, okay? So we also then have to do a horizontal rotation. And that's going to get it in the pointing out towards us direction, right? We don't normally write these where both of them are out of the plane. Which, thank goodness we don't, right? Does that look like something you'd want to write all the time? No. That seems annoying. And so this is actually what we need to do in terms of rotations, okay? Okay. Now, notice that this one right here is going to be the one where it's at the bottom of the valley. See that? So here we have it pointing upwards like a triangle. Let me do these rotations. This one right here is where it's already on the top. This is what it looked like when you rotate. So you rotate it here and it's on that side, doesn't it? Then we rotate it this direction instead. Okay? And that ends up pointing away from you now. So this is the 2 different possible rotations that we could end up doing here. See that? Okay. Okay. So we have the one where the W is on top here, and our carbon is the bottom of that valley right there. We have the one here where the carbon's the peak, right? This is the base of the mountain. Okay. Okay. What we notice here is when this one, where we rotate it like this, where we have it at the base, is rotated, this X that was coming out towards us, this is always going to end up on the left side. The one going away from us is always going to end up on the right side. Okay. The one where the W here, the thing we're rotating to the top, is on the top. Yeah. We're going to end up rotating it, and what we notice is the thing that comes out towards us ends up on the right side this time, because we rotate the exact reverse directions, don't we? See that? This part doesn't cause a lot of chaos, but this part is where we get completely different behaviors, don't we? Okay. And so that's how that 3-dimensional rotations work. So let's go ahead and look at this in terms of doing this entire structure, okay? So this is our end of the molecule. It's going to end up on top. Everybody good with that so far? Okay. Okay. So this one here is a peak, right? See how it comes up from that end? And we form a peak. Okay? And so the one that comes out towards us is going to appear on the left side. When we have the valley, the one that comes out towards us appears on the right side. Peak again. One coming away from us this time, right? If it's coming away from us, then it has to appear on the right side. Okay? Peak, coming towards us, left side. Coming away from us, right side. Okay? If it's the valley, it's the opposites, right? Okay. So let's go ahead and look at this real quick. Peak towards us, left side. Valley towards us, right side. Peak away from us, right side. Okay. Now, when we have Fisher projections, we can actually flip these back and turn them back into zigzag structures. Okay? It's just the same rules, but in reverse now. Right? And so this would be our stereocenters again. This is 1, 2, 3, 4, and we have our stereocenters. Okay. The first thing we need to do is, we need to make our backbone. Okay. You're always going to want to write this so that your high priority group right here ends up falling over to the left because English goes from left to right. Top to bottom, left to right. It's just English orientation. And then we are going to number again, 1, 2, 3, 4. Notice that this is always going to be the valley, right? Why is that the valley, by the way? Because these are going away from you, aren't they? Okay. So you always want to put this in the valley. Come up, down, down. Okay. Does anybody know what would happen if I went the other way? Notice I always write that way anyways. Because I've been around the block for a while. But hopefully you too start writing like that. What would happen if I went like this? I'd flip all my configurations. When I did this, if I used the same rules, I'd actually just flip everything. Okay? Okay. I would very likely end up with the opposite enantiomer if I do everything correctly. Okay, so let's go ahead and look at how do we get this now. Now, the top of the Fisher projection, we end up on the left of the zigzag structure. We start at the bottom and go up to a peak. So the next one's a peak. So if we have it on the right side, right, this is going to end up being a dash. Because remember your peak assignments? Okay. If we have the next valley here, it ends up on the left side, that's going to be a dash again. If it was on the right side, it would have been a wedge coming down towards us, right? Okay. Notice you really just need to get like one of these memorized. As long as you can figure out one of them and be confident in it, yeah, everything else is reversed, right? Yeah. So just make sure you have like one set of this where you really understand, and then you can work your way back. Okay. So constitutional isomers have different physical and chemical properties. And so again, this is constitutional isomers. We have the pent-1-ene and the pent-2-ene. And see how they have different boiling points? And so if you wanted to separate these, you could literally just boil one from the other. Okay, that's distillation. Again, here we have a very different boiling point. See that? These would be really easy to distill one from the other, wouldn't they? Okay. And so they have to have pretty different physical properties. They're oftentimes also going to have different chemical properties as well. And so, for example, this one would have different chemical properties than this one, actually. This one has an acidic hydrogen here, in case you're wondering. Okay, so enantiomers are going to be mirror images. They're going to have the same connectivity, precisely the same polarities. They're going to have the same boiling points. Almost all of their physical properties, assuming you don't have anything else that's chiral in there, is going to be the same. Exactly. Everything's the same. Yep, you got it. Yeah. It really doesn't matter. However, is there a difference between a right-handed and left-handed mouse? Or a right-handed thumb? Nobody knows that? Yes, there very much is a difference, isn't there? If you use a left-handed scissors or right hand, it really is unpleasant. If you use vice versa, also very unpleasant, right? And so there is a big difference, isn't there? Okay? So when you don't have anything else, all other things being equal, and you just have a racemic mixture, you're going to end up with same properties, okay? It's only when you start actually having a different environment that is chiral that these things become separable, okay? So right here, we see a plane of symmetry right here in our socks, and so our socks actually can fit on either foot, right? And so most socks don't have a right-left configuration, okay? At least the majority don't. And that's because they have a plane of symmetry. And so again, achiral environments and enantiomers are going to have the exact same physical and chemical properties. There is no difference, right? That's the same for like a bat, by the way, because it's symmetric, right? It doesn't have a difference. Okay? But if you have it asymmetric, the same way as a shoe. So in a shoe, we've actually created an achiral environment. Our environment itself has chirality. Okay? Most environments typically are achiral, like your flask, achiral. Most environments, achiral. Socks, achiral. Exactly. Shoe is a chiral environment. So if I try to stick my left foot in my right shoe, it doesn't work, does it? And so the most common chiral environment you're ever going to identify is biological. So biological organisms are a chiral environment. Everything in us is chiral. Okay? Very few things in a biological environment are achiral. It has to do with almost all of our groups are tetrahedral. So when you start like looking at proteins, all the amino acids are tetrahedral with 4 more things. And so we're making all these proteins and enzymes that are chiral by definition. And so when you start looking at biological systems, like the different chiralities, like I was mentioning, some are poisons, some are flavorings. You can have completely different flavorings. The birth defects we were mentioning, those are all a consequence of being us, humans, being a chiral environment. Yeah. Versus an achiral environment where it wouldn't matter, right? Okay. And so, yeah, in a chiral environment, they will actually have different physical properties. They'll have different bindings. They'll have different boiling points even. They'll have... Exactly. Depends on what you're hydrogen bonding to. So if you take like a chiral, if we had like a chiral solvent, one of the chiralities could end up dissolving better than the other. And it could end up easier to boil off than the other. Yeah. So we have all those consequences. Exactly. In fact, you can do this. You can separate enantiomers only if you have a chiral environment. If you have an achiral environment, and that's actually how you can do like separations of like enzymes and proteins and stuff. So a lot of those separation techniques use a chiral environment to do it. Anyways, diisomers, these have different physical and chemical properties, again, because they're not going to be mirror images of each other, right? So you can actually see that very nicely here. This is polar because the chlorines will contribute in the same direction, right? Versus this one here where the chlorines actually cancel each other out, so that ends up being nonpolar. And so this right here is a polar aprotic solvent. This one right here would be a nonpolar solvent. Okay. This right here, again, these diisomers right here would actually have very similar properties because, again, we end up with that sort of reflection. But notice they're a little bit different. Okay. The more symmetric they are, the less difference in the properties you're going to get. Okay. So the more asymmetric they are, the more difference in the properties you're going to get. And so here we actually have a meso right here. And so the two different forms of the meso are the exact same molecule, right? They have absolutely no difference. It doesn't matter what you do. Okay. This right here, again, we have diisomers of each other. They have very similar properties, though, because we end up with them on the same pulling directions, don't we? So they match up mostly. It's just a very tiny difference there. And so they do have a different boiling point. It's just really small, right? It's unlikely you're going to be able to distill those from each other, but you will get some separation. Like you tried to distill them, you might change it from 50-50 to like 40-something% instead. Okay? So you can get a little separation, but it is very similar. So Louis Pasteur was actually the first to isolate a pair of enantiomers from each other. Everybody kind of knows pasteurization and nothing else about Louis Pasteur, which is funny because it's like he did a lot of stuff actually. He's very prolific. And this is one of those things. So Pasteur actually noted that crystals grown in one of two varieties. When he was looking at a sample, he had left-handed crystals and right-handed crystals, and that they were mirror images from each other. So you can actually tell the difference between the two, and because they're crystallizing, they want a very, very set pattern where they're not moving around, right? And so they literally crystallize as different crystals with different orientations. Okay? And so you can take a microscope and tweezers, and you can quite literally pull these layers apart and separate your different enantiomers here, your different chirales, which is kind of cool, right? Yeah. Okay, and so that was actually the first ever recorded separation of enantiomers. Their physical properties, again, are just different enough that when they crystallize, they're going to crystallize into two separate samples. Okay. There's actually a bunch of methods for separating enantiomers. One of the main alternative methods for separating enantiomers is going to be like temporarily converting the enantiomer into a pair of diisomers. So if you convert them into diisomers and they have different enough physical properties, you can then separate them with, distillations and just your normal separation methods. Okay. And because they're different forms, if you do a reaction, they're going to have different diisomers. Okay. You can separate the diisomers from each other by exploiting their different physical and chemical properties. For example, these crystallize in different patterns, and so they'll form two different crystals that you can then pull apart. Okay. You can regenerate the enantiomers from the separated diisomers then in this alternative method. Now, this is kind of an old school alternate method. This is it takes a lot more steps, and there's a lot more purifications, and you lose a lot more. There's actually a newer methodology where you actually make targeted enantiomers that bind to a specific enantiomer. So you basically make your own little enzyme or protein that binds to the thing. And you can do this with antigen systems. You can actually inject it into mice and have them form antigens to it. There's a bunch of ways you can do this, but essentially you form your own chiral system, and then they'll bind differently to the system depending on the enantiomer. And so one will go through faster, one will go through slow. And so you can actually separate them like basic chromatography, where you just run them through a column. One will go through fast, one will go through slow, and you get separation. Okay. So there's actually a lot of progress that's been made over the last 5 to 10 years on separating different enantiomers and really mastering this process. It's kind of a neat thing. And putting them down into solids and materials very, very selectively. So you can actually selectively put down enantiomers and change the heat flow characteristics. So whether heat flows one direction versus the other. And make materials where heat selectively flows one way and not the other. Okay? So it's kind of cool. Optical activity, this is how you typically test these materials. This is actually what we're going to be doing Friday. So we take chiral molecules, they're going to interact with plane polarized light differently. Okay? Does anybody know what plane polarized light is? So light travels in different planes, right? And so it can travel in different planes. All photons from a light source have electric fields. They operate oscillating. Exactly. They're operating the same field. So right here we have the electric field. Here's we have the magnetic field. When you look at light outside, it's typically not plane polarized. It's depolarized. It has a bunch of different orientations. When you look at it through a sunglasses or you look at an LED, that's typically polarized. Anybody had their sunglasses on and they try to look at their phone and they get that angle and it really dims a bunch? That's what's happening. Your polarity of your sunglasses is matching up in that magic orientation with your phone's polarity that's blocking most of the light. And that's how sunglasses work. They actually block out one of the planes of polarity. Okay? Okay, so this right here is a polarizer. Most light sources are actually unpolarized, though not in modern day because a lot of LEDs. LEDs are polarized typically, unless they're designed not to be. A polarizer is going to generate plane polarized light by filtering out light whose electric field oscillates in the other plane. You guys have seen those sunglasses where it's like straight lines? Or the like little things you can look up at the overlapping of the sun and the moon, or straight at the sun, period, and not get your eyes burned out. Okay. And you do it by like putting little lines, right? That's a polarizer. Okay. And so this right here would be plane polarized light. The only light that's coming through in significant quantities is this one that matches up with this plane here. Okay. And the other lights get blocked in significant quantities. So if you use two of these, you can actually polarize your light. Oh, I guess I have to stop. I'll start up here next time. We'll talk about the polarization of light, and it'll be fun because Friday you get to do this using a polarized meter and actually find your optical activity for your sample next time. You all have a great one. We'll see you Thursday.
About the exam. So I don't remember exactly what question it was, but I think it's like 19 or something on version B.
Mhm.
And it's asking about IUPAC naming. And you remember how we talked yesterday about like priority
Mhm.
experiments?